When doing predictions, we're used to using linear regression or multiple linear regression for prediction. However, there are times when we use linear regression where the answers will not be good because our dependent variable, the y variable, isn't a continuous number. But there are many important research topics for which the dependent variable is limited and is not a continuous variable. For example, voting, yes or no, morbidity or mortality, and when participation data is not continuous or normally distributed. Binary logistic regression is a type of regression analysis where the dependent variable is a dummy variable coded as a 0 or 1. Now, before we look at logistic regression, we must consider how we can predict a variable that is coded as a 0 or 1. Predicting a binary variable is really an extension of a probability or likelihood of an event occurring. Odds, therefore, are simply the probability of an event occurring. And so that's what we're looking at when we have a 1 or a 0. What's the probability of getting a 1? What's the probability of not getting a 1? Now, for example, in a horse race, let's assume the odds of a horse winning are 8 to 1. This means that the horse will win one race for every 8 races it loses, in a total of 9. So the probability of winning is actually 1 out of 9. How do we then view an odds ratio of 8 to 1 losing? To calculate an odds ratio, we simply need to create the ratio of the odds of winning to the odds of losing. Assume our probability of winning the race is 1 over 9. Then our probability of losing the race must be 8 over 9. Therefore, the odds ratio becomes the probability of winning over the probability of losing. And here we see that formula. We take the probability of winning, 1/9, and we put it over the probability of losing, 8/9. Using a little algebra, we end up with 1 over 8, which is 0.125. So the probability of winning is 1/9, or 0.11, but the odds ratio, or just odds of winning, is 1 over 8, which is 0.125. Now, what if we were to look at the odds of success versus the odds of failure? If we look at this on a graph, we might actually see it curve, where, for example, in this case, we have the number of hours studying related to the probability of passing an exam. So across the bottom axis, we have the hours of studying. Along the left, we have the probability of passing the exam. The dots are actually indicators of whether or not the student passed at a 1 or did not pass at the 0 based on the number of hours studying. And we could see that if they didn't study that many hours, let's say less than 1 or between 1 and 2 hours, it looks like many of them did not pass the test. But as we got closer to 4 hours and 5 hours, it looks like many of them passed the test and no one failed. The probability curve that's actually created out of this is known as a sigmoid curve. Notice how it's a clear S shape, and it shows the probability of success, 1 at the top, and failure at the bottom. The further we were to the left, the more likely we were to not pass the test, and the further we were to the right was the more likely we were to pass the test. Therefore, we need a method that would help us identify when a success or failure will occur, and determine what factors might help us predict an increase in odds. This is known as logistic regression. So logistic regression is a regression model where the dependent variable is categorical, specifically a binary 0 or 1. So this means that the binary 0-1 dependent variable is represented as a binomial logistic regression. And we can also use the same type of regression to do a rank ordinal dependent variable, and that would be an ordinal logistic regression, where we were trying to predict rank of, say, 1, 2, 3, 4. Now, why can't we use a standard linear model? Let's assume that we have this format for our linear model. We have a y hat, which is our predicted value, our beta coefficients times our x variables, plus an epsilon for error, where y hat must be between 0 and 1. So the predicted values in a linear model could be less than 0 and greater than 1 because it creates a line. The error terms would not have constant variance. They would be heteroscedastic. Further, the error terms could not be normally distributed because y only takes 2 values. So therefore, our errors would not be normally distributed. And these are violations of linear regression assumptions And so therefore we do require something different. The Logit model solves these problems because what we'll end up doing is we'll create a regression formula here to the right where we have the beta coefficients times the x variables plus an error. But instead of doing a y-hat, we're actually going to use a log model where we're going to do log with the probability of p over the probability of 1 minus p. So that's equivalent to the probability of success over the probability of failure. So p represents the probability that the event y occurs, the probability that y equals 1. P over 1 minus p, therefore, is the odds ratio. And more specifically, log of p over 1 minus p is the log odds ratio, or the logit. The logistic distribution therefore constrains the estimated probabilities to lie between 0 and 1. So therefore, the estimated probability is going to be p equals 1 over 1 plus e raised to the negative exponent of the beta x plus epsilon. So notice here that this part is our regression equation. It's the beta x plus epsilon. And so therefore, this estimated probability is actually based on this formula where our exponents, where our coefficients are merely an exponent of the natural e in the denominator of this formula. Alternatively, we can state that our coefficients of the regression are in that beta matrix, and therefore the formula expanded out looks like this. So let's take a closer look. In this case, we have p equals 1 over 1 plus e to the negative, and this is our regression equation. If the coefficients are not statistically significant, then each term, beta I xi equals 0. In this case, we would end up with p equals 1 over 1 plus 1, which would yield a p equal to 0.50. We have an equal chance of success and failure. If the terms beta I xi are really big, then p will approach 1. If the terms beta I xi are really small, then p will approach 0. Therefore, this equation bounds p to a number between 0 and 1. Now let's compare a linear line and a logistic model graphically. The black line shows the logistic regression line, and it represents the probability of success or failure for a given value of x. The red line would be a linear regression line, and we could see that in that linear model, we don't have this asymptotic point at the bottom or at the top, that it approaches 0 or approaches 1. The red line would actually go through it. The points on the dashed lines actually represent the actual values from the data as 1s and 0s. And we can see that we shouldn't have anything greater than 1 or less than 0. Now let's take a look at an example in R. Suppose we want to examine the admission of a student to a university based on the following information. We can determine the increased odds of admission with unit increases in the independent variables. So to the right, we have a sample piece of data. The focus is to identify what factors will lead to an admission. Therefore, we may have an admission variable as binary, 0 not admitted, 1 admitted. The other variables are the predictors or the independent variables in the equation. When we run the logistic regression using R, we're going to use the GLM function. The GLM function takes in a formula as its first parameter. Here it's going to be admit by GRE plus GPA plus rank. And we tell it where that data can be found in the MyData data frame. Further, we specifically specify the family as binomial. We're telling the GLM model, which stands for Generalized Linear Model, we tell it specifically that the family is binomial, so it should treat the dependent variable as a binomial. When we run this, we will get an object. We will then take the summary of that object to get the resulting output. And the output then, in some ways, is similar to the way we saw our linear regression. So based on the information that is provided, we can see here that all the variables are significant. such that p is less than 0.05. Recall that the hypothesis test is done for each of the variables, such that the beta coefficient is equal to 0, and the alternative hypothesis is that the beta is not equal to 0. So therefore, when p is less than 0.05, we state that we have enough evidence to support the fact that the beta coefficient is not 0, and thus it's significant. Now, in addition, we will look at the estimate. The estimate now provides us the log odds increase or decrease of admission. So therefore, here with the log odds, pointing here at the GPA variable, which is 0.80, this would be a log odds increase of admission based on a unit increase of GPA as being 0.80. The estimates that were provided are log odds, and it's not really sufficient or clean enough to report data as log odds. People wouldn't understand what you're talking about. So therefore, if we compute e to the power of each of the coefficients, we will obtain a more interpretable number. This procedure will provide the odds as more likely or less likely. So we use the exp function in R. exp, open parenthesis, coef, which is for the coefficient of our object that we actually created from the logistic regression. And you'll see here that we have 1.002 for GRE, 2.23 for GPA, 0.50 for rank, 0.26 for rank 3, and 0.21 for rank 4. So the example above shows that for every unit of increase in GPA, the odds of admission increase by a factor of 2.23. Additionally, if we look at the rank 2, a student of rank 2 is 1/2 less likely to be admitted than a student of rank 1, which is the control. So you'll notice there is no rank 1, and that's because it's used as the control in that equation. When we have a factor in our model, the first value in order will be the control. Each of your categorical levels, rank 2, rank 3, rank 4, will be compared to the control. So some examples, we might consider to use logistic regression to determine things like the odds of a customer downloading a product, the odds of moving up in rank for mobile data, the odds of fraudulent traffic, the odds of contracting a disease, or the odds of passing a class. Let's take a little deeper look at something. The cumulative distribution function of the standard normal also follows a sigmoid curve, and as such is an alternative sigmoid function for use in the logistic regression. So recall that we are looking for a sigmoid curve that would basically match this pattern of asymptotic to 0 or asymptotic to 1. The standard normal curve is shaped like a bell curve, but recall that the values on the x-axis correspond to a z-score. In this case, below, a z-score of 0 represents 50% below the mean, and above, a z-score above 0 would be 50% above the mean. The Probit model is a different logistic model that uses a different function for computing that sigmoid curve, which is necessary for probabilities between 0 and 1. We assess that y is a probability from 1 to 0, given a set of independent variables. So here's our formula again, where we have y hat equals beta 0 plus beta 1 x1 plus all the way to beta n xn. The probability of success is given as a function of the cumulative standard normal. So therefore, we have the probability that y equals 1, given the fact that we have x1, x2, all the way to xn, is equal to this function phi, beta 0 plus beta 1 x1 all the way to beta n xn. The interpretation here is that the beta is the effect on the z-score, the standard normal, of a unit change in the regressor x holding all variables constant. So what we're saying here is that we're looking for the effect on the z-score. Now remember that z-score followed that normal distribution, right? That standard normal, and its cumulative distribution function was not the bell curve, but a sigmoid curve. A cumulative distribution is adding up all the probabilities, where all the way to the left it's 0, and then all the way to the right it gets closer and closer to 1 because it's the cumulative distribution function. So here, we're looking for the fact that we're going to interpret each coefficient as the effect on the z-score. Will it move up or does it move down? For a unit change in a particular independent variable or regressor, if all of the variables are constant. So this equation determines the effect on the z-score. Each beta coefficient measures the effect on the z-score, which is done by taking the inverse score. So for example, z equals phi beta 0 plus beta 1x1. The z-score would equal phi negative 0.0451 plus 0.0903. In this case, the interpretation of the x1 coefficient, 0.0903, is that for each unit increase of x, the z-score will increase by 0.09. However, the impact on the probability that y is 1 is different at different points. So let's review the normal curve again. Let's take a look at the following probabilities. If we look at the area of a particular number for a particular z-score, let's say -1, the area between -2 and -1 is a lot smaller than the area between -1 and 0. Because again, as it gets closer to the mean, the amount of area is much bigger. So the values are obtained by taking the inverse of that z-score. So in R, we would do p norm x, the value, mean 0, standard deviation 1, for our standard normal distribution. So if we take the probability of z equals -2, here at the bottom left we have a corresponding chart. That's equal to 0.023. Now, a 0.5 increase in that z-score would basically give us z equals -1.5, which the area is now 0.067. That's represented by the second chart. The difference between the two is 0.044, so there's a 0.044 increase in the probability. If we increase by a half again for that z-score, we'll now have z equal to -1, which is 0.159. The third chart shows us we have a lot more area that we've now covered, just for that same 0.5 increase. And so therefore, the delta is actually 0.092. We've increased by 9%. If we increase again to -0.5 for the z-score, our delta now moves to 0.150 because we are increasing in the total amount of space. So using the same example of running a logistic model with admissions, we can run the following code. We have our model, GLM admit by GRE GPA as factor rank, data equals binary, family equals binomial Probit. We're specifically saying we would like to use a Probit model. When we get the summary, our results are similar to the Logit model, but have different values. We can see here, if we were to compare this to the previous one, again, all of the values of the coefficients are significant because all the p-values are less than 0.05, but our coefficients are slightly changed. Each estimate here represents the change in the z-score for each unit increase in the variable. If we were, instead of before taking e to the coefficients, we're going to take the p norm to the for the coefficients. We end up with the following. We're going to do round, only because we want to round it to the 3 decimal places. P norm of the coefficients of the model, again, using 0 and 1 for the mean and the standard deviation. And this will now give us the value that we want. Therefore, for each unit increase, say in GRE, the probability that y equals 1 increases by 50%. And for GPA, for every unit increase in GPA, the probability that y equals 1 increases by 68%. For categorical variables, it's a little different. In this case, we take the rank of 2 and the rank of 3 and the rank of 4, and we say that the probability of admission for a rank of 2 is 33%, whereas the rank of 3 is 20%, and the rank of 4 is 17.5%. Now, the results between the Probit and Logit models are nearly identical. If we were to plot the lines, which we've done here, the red line and the blue line show that there's not much difference. The Probit is the red line, the blue line was the Logit model originally. And we could see that the lines are almost identical. You could see a little deviation down at the bottom there. The Probit and Logit models will provide the same significant coefficients. The probability values are therefore similar. The difference between the two is the nature of the sigmoid curve. The Logit curve has slightly fatter tails than the Probit curve. The use of each is based on the domain. Econometric models generally use the Probit models, while natural sciences use the logistic model, but there's really little difference in the results. Now we can predict with the logistic regression as well. Recall that each of the models produce an equation, the Probit and the Logit. Therefore, a prediction of the probability for each of the variables will simply be replacing the betas with the appropriate coefficients derived and the values of the x variables. Using our logistic model for the admission logistic regression, we can create the following equation. The coefficients have been binded in a data frame so that we can easily review. So here's our Logit model, and here's our Probit model with the appropriate coefficients. If we wanted to compute something for any given GRE, GPA, rank itself, we could actually use these coefficients in these equations to compute the probability of y equals 1. But we can also use the predict function in R, so we don't have to do this manually. We use the predict function in R to obtain predicted values for each equation. So to use the predict function, there are 3 parameters. MDL, which is the model that we just ran, and new data, which is an optional parameter, but if we supply it, it will use the variables of a new data set to create probability predictions, and the type. If we set this to response, type equals response, it will output the probabilities in the form of P y equals 1 given x. In other words, it's going to give us the actual probability. Therefore, running predict for our 2 models, using the original data, we obtain the following first 10 predictions. So we ran our model 1 here using the Logit, and we ran model 2 using the Probit. In between each, we basically ask for the prediction based on that model. Any prediction greater than or equal to 0.5 will be a 1, otherwise it's a 0. So here, we've created this data frame so that we can see what it looks like. The predicts will give us the Logit probabilities and the Probit probabilities. What we've done here is we've just indicated whether or not it would be a 0 or 1 based on that 0.5 criterion. So as we can see here, the Logit predicts 0.17 and the Probit predicts 0.17 as well. In the next case, the Logit predicts 0.292, the next one predicts 0.295. And you'll see all the numbers are very close to each other, off by 0.002 or 3 in that vicinity. And so the numbers for the predictions generally match, where they would be a 0 or a 1. Now, its accuracy is really going to be based on whether or not the Logit predicted an admit and the actual was an admit. Let's see how we can look at those. By creating a table of matches, the 2 methods we can see are clearly identical, and they have the same basic error rate. What we do is we create this cross-tabulation to determine when the logistic model predicted a 0, was the actual a 0? And in this case, we see that 254 times that was correct. And when logistic predicted a 1, did we admit predict a 1? And that was 30. Both the logistic and Probit models predicted the same number. But our error rates are based on the fact that 19 times we were wrong when the logistic predicted a 1 and the admit was a 0, and 97 times it predicted a 0 when the admit was a 1. Normally, we'll use percentages to determine the overall accuracy rate. Now, the deviance residual measures provides a means to determine the fit of the model. Recall that in standard linear regression, the use of an f-test will determine whether a model has overall utility. In logistic regression, we will examine the deviance residuals of the null model against the defined model, and the output provides the following summary. Here we have a null model of 499 with a residual deviance of 458. We can actually use the chi-squared distribution to determine whether or not this is significant. So when we take the probability here, using p chi-squared, of the null deviance minus the model deviance, we have a degrees of freedom, which is 5, and a lower tail equals false because we're only concerned with the upper tail in this case. We end up with a p-value of 7.5 times 10 to the negative 8th power. If the p-value is less than 0.05, then we could say that the model is statistically significant. What you'll notice from here is that the residual deviance will be smaller than the null deviance. So what we're trying to determine is whether or not it is small enough to say that there is a statistical difference between the two models. A couple of other things that we can do here for logistic regression is we have the pseudo R2, which is analogous to R2 in a linear model. Now remember, we don't have a true analysis of variance in our logistic regression, so we're basically using pseudo R2 as a measure of this fit. There are three methods that we can use: the Cox-Snell R2, the McFadden R2, and the Tjur R2. Cox-Snell compares the log likelihood of a model to the base. The log likelihood is a formula to determine how something is likely to appear, but it uses a log function to do that. The problem is that it has its theoretical maximum of less than 1, so there are some issues with that. We have McFadden's R2, which provides a ratio of the model to the base, and it's more conservative. A number between 0.2 and 0.4 is generally a good fit. And the Tjur R2, probably the simplest of the R2, takes the mean of the predicted probabilities and subtracts them. It cannot be used for any other models other than binary outcome. These values are really to be used to compare models more so than anything else, and should be interpreted as such. So you're not using it like the traditional R2 where you say the percent of variance in Y explained by the regressor models. Here what we're doing is we're taking an R2 of one model and comparing it to an R2 of another model to determine if it's better. In R, we're going to load the package DESC tools, and then the pseudo R2 can be computed using the pseudo R2 function, or R2 function. So in this case, we have the pseudo R2 of the model, Cox-Snell, and we do it again, pseudo R2 model 2, Cox-Snell, and we could see that the first one is 0.0984, and the other one is 0.0986. In the second case, we have two models here, again McFadden's, and we have 0.0829 and 0.0831. And the Tjur model here, we've got 0.1017 and 0.1016. We do want a higher R2 value, so two of them actually indicate that model 2 is better. One is actually indicating that the other one is better. And which one you use is actually up to you. However, at the end of the day, you'll find that when you do your predictions, they're going to be identical. And this is one of the reasons why it's almost immaterial as to which method you're using, because you will get the same results. The difference here in what we're showing with the R2 is that the models are generally the same. We just used Probit versus Logit. Where you'll see these R2 giving you differences is going to be when you have a model that, say, has 3 variables as opposed to 5 variables. And that's what you're trying to use this R2 for.